All right. Hey there, Trigs. So today we're going to look at composition and we're going to look at inverses. Notice we have two objectives. The first one is students will use algebraic procedures and properties of composite functions in order to evaluate and derive formulas for composite functions. The second objective is that students will use the properties of inverses and the horizontal line test in order to determine if the inverse of a function is in fact a function. We got some homework there. First, we're going to just do a little practice here with composite functions. So we're going to say that m of x is the mother of x, and f of x is the father of x. So the question is asking us, what is the f of the m of Elizabeth? So in other words, Elizabeth Ann is our x. So what we're going to be looking at is, we're starting at the child, okay? Starting at the child, which is Elizabeth Ann. Then it says, what's the f of the m? Well, which one do we do first? Do we do the m first or we do the f first? Well, since we started with Elizabeth, we're starting on the inside, where we always start. We start with our x, we're starting on the inside. So we want to find the m of Elizabeth first. M stands for mother. So the mother of Elizabeth, Elizabeth's mother, is Susan. And then we want to know the father of Elizabeth. Well, Elizabeth Ann's mother is Susan, so the father of Susan is Dale. So the answer to that question would be Dale. Yes, Elizabeth Ann is my niece. Dale is my dad. Susan is my sister. I'm not on here because I did not have children. The next question says, m is the mother of x and f is the father of x. So this question says, what is the f of the m of Susan? We can't do the m of the f because then it looks like you're saying mf Susan, so we don't want that. So we've got the f of the m of Susan. So we're starting with Susan. We want to find the mother of Susan, who is Peggy. And then we want to find the father of Peggy, who is Sherd. So these are composite functions. Very simplistic composite functions, but composite functions nonetheless. Okay, and the last one, Mark is my brother-in-law. We want to find the mother of the father of the mother of Mark. So we start with Mark. We find his mother, who is Shirley. We find Shirley's father, who is Arthur. So we've got Arthur is Mark's grandfather. Okay, so what we're looking at is we're looking at composite functions. So what you need to do is you need to take a second and you need to jot this definition down. Okay? It says, suppose f and g are functions. The composite function, the composite of g with f, written g circle f, is the function defined by g circle f of x, which means g of f of x. The domain of g circle f is the set of values of x in the domain of f for which f of x is in the domain of g. So in other words, when we see this notation, okay, this g circle f, that means g following f. So you do the f first, which is just the same reason why you can write it and just take and put parentheses here. So you could say g of f of x, which means you're going to start with your f of x first and work your way out. Then it tells us that the domain of g following f is the set of values in the domain of f for which the y values are in the range of g, or in the domain of g. So in other words, it's the domain of f such that the range of f is in the domain of g. So how do we do that? Well, finding the domain of a composite function is the set of all elements for which g following f is defined. So be in the domain of g following f, a number must be in the domain of f, and the corresponding f of x, the corresponding y value, has to be in the domain of g. So it has to be a number that works in the f function, so it has to be in the domain of f. And the range value of f has to be in the domain of g. And so we'll take a look at what we're talking about there. Okay, so but first, how do we find a composite? Well, to find a composite, we're asked to do two things here. We're first asked to find f of g of x. So that means we're going to take the g function. which is 2 divided by x plus 5, and we're going to plug that in for x. So we're actually going to do f of 2 divided by x plus 5, which means we're going to take 2 divided by x plus 5.
Tamia Cumberland, your right is out front. Tamia Cumberland, your right is out front.
And then that gets subtracted by 5. So all we did was we took this value right here, which is our function for g, and we plugged it in for x. That's how we find composites. So now we do the algebra. Well, dividing fractions is the same as multiplying by the reciprocal. So this actually is the same as saying 2 times x plus 5 divided by 2 minus 5. Well, our 2's cancel out, so we have x plus 5 minus 5. The 5's add out, so that means that f of g of x is x. This helps if I write it in the right order. So f of g of x was x. Doesn't always equal x, but at this time it did. So now we're asked to find the other way. So the other way now says we're going to take and we're going to put the f function into the g function. So we're going to take this f function here and we're going to plug that in for x in this function. So to do that, we're going to do g of 2 divided by x minus 5, which means we're going to have 2 divided by x minus 5. That's our x value now, plus 5. Okay? Well, there's nothing happening to these parentheses, so we can just combine like terms. So we have 2 divided by x minus 5 plus 5. The 5's add out, so we have 2 divided by x. And again, dividing fractions is the same as multiplying by the reciprocal. So we have 2 times x divided by 2. The 2's cancel, so that leaves us with x. So this time we know that g of f of x equals x. Bonus question. Because f of g of x equaled x and g of f of x equals x, does anybody know what that tells us about f and g? Well, hopefully you will by the end of the class. Okay? So, taking a look at our next example, we're supposed to find the composite of each. Now, this is the same deal. It says evaluate each composite, but this time it has a number. So the first thing we're going to do is we're going to plug 1 in for g. So when I plug 1 in for g, that's 3 times 1, which is 3, minus 5, which is negative 2. So my next step is to do f of negative 2. So when I do f of negative 2, I've got, second quit, and I'm going to just store negative 2 for x, so I don't have to keep typing negative 2 all the time. And I've got x squared plus 7x plus 2. And I press enter, and it tells me that my answer is negative 8. Well, yay! All right, you try the next one. Good job. Now this last one asks us to come up with a formula for each. So it's like we just did on the previous slide. We're going to take g of x and plug it in for x in each one of these. So we're going to take g of x, which is 3x minus 5 squared, plus 7 times 3x minus 5 plus 2. And we're going to simplify this. So when we expand 3x minus 5, we've got 9x squared minus 30x plus 25 plus 21x minus 35 plus 2. Combine like terms, you got 9x squared. Negative 30 and a positive 21 is a negative 9x. 25 minus 35 is negative 10. Negative 10 plus 2 is 8. And it's a negative 8. And that is what the textbook says. Now the second question says to find g of x, which means we're going to do exactly the same thing, but we're going to take the g function, which is 3x minus 5, and we're going to put it in to the g function. So we're going to have 3 times 3x minus 5 minus 5. So we've got 9x minus 15 minus 5, which gives us 9x minus 20. Now, when you look at these two, they didn't both give us x this time. So whatever relationship those other two had, it's not the same as this one. So these are just composition functions. The other two were much more special. Okay, now this one's a little awkward. It's asking us to consider it using mapping notation. H maps A to B, and B to C is mapped by J. So it says here J of W. So we're starting with J, so we're starting in B with W, and W gets mapped to W, and then we do the H, and W gets mapped to X. Okay, so this time we start on the inside, we have H of X. So H of X, X gets mapped to Y, and then we do the J, and Y gets mapped to Z. And then lastly, we have H of J of X. So we're going to do J of X, so X gets mapped to X, and then X gets mapped to Y. Oh, it was a Z. Sorry. That was a Z. So when we're doing Z, J of Z, Z gets mapped to Y, and Y gets mapped to W. Sorry, it helps if you can read the letters. That's my bad. Okay, now when we do compositions of transformations, because we've done scale change transformations and we've got translations transformations, we're going to do a simplified form for this. And so what we're going to do is it says that the scale change is x and 2y, and the translation is x minus 3 and y plus 4. And it says we're going to write a simplified form for t following s of xy. So that means we start with our s. S is where we start. So we're going to have to do t of whatever our s function is. And for us, our s function is x and 2y. Okay, so we're going to take that x and 2y and we're going to replace it for x and 2y in the translation, which means instead of x minus 3, it's going to be x minus 3. And instead of y plus 4, it's going to be 2y plus 4. And that's going to be our translation. Now, what if it had been reversed? What if it had been s following t of xy? Well, we would have started with our translation, right? So we would have had s of our translation, which is x minus 3 and y plus 4. and then we would have substituted those into the scale change. So instead of just x, our scale change would have been x minus 3, and our y, instead of 2y, it would have been 2 times y plus 4. So that means the end result here would have been x minus 3 and 2y plus 8. Okay? So it does matter the order you compose. Now we're going to talk about our inverses. Inverses are when you switch the coordinates in a set of ordered pairs. The resulting coordinates are the inverse. So this is xy, 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 xy. This happens to be a parabola, right? Surely you recognize that this is y equals x squared, or f equals x squared for those numbers. So there's our x, we square it. There's our x, we square it. So to find the inverse, we're going to start with 9. So we're just going to switch the order of things. So instead of it being negative 3, 9, it's going to be 9, negative 3. Instead of it being 4, negative 2, instead of being negative 2, 4, it's going to be 4, negative 2. Instead of it being 1, negative 1, you're going to switch the order. So this is what your inverse looks like. To find the inverse, all you do is you switch the coordinates in a set of ordered pairs. Now that's beautiful if you have a set of ordered pairs. But what if you're given the function? Okay? Well, when we're given the function, if we plotted those ordered pairs that we just had, we had negative 3, and it was 9. Then we had negative 2, and it was 4. We had 1, 1. So these were our ordered pairs, right? So that's our original function. Our inverse, instead of negative 3, 9, we had 9, negative 3. And then we had, instead of negative 2, 4, we had 4, negative 2. Then we had negative 1, 1, so now we have 1, negative 1. Then we had 0, 0. Then we had 1, 1. Then we had 2, 4, so it's going to be 4, 2. Then we had 3, 9, so it's going to be 9, and 3. So when you look at the green dots and you look at the orange dots, how are they related? Yes, that line is the line y equals x. Good job, good job. So if that's the equation and that's the graph of the line y equals x, why would I have that on there? Right, because remember we switched the x and the y's. So basically what we did is we reflected these dots over this line. That's what happened. When you reflected here, it became there. When you reflected there, it went there. When you reflected here, it went there, and so forth and so on. So each dot is a reflection over the line y equals x. Because when we want to find the variables, we just switch. When we want to find the inverse, we just switch our x's and our y's. Interesting. We don't need that line there, so let's just throw it away. All right, so then it says, if you switch the variables in an equation, the resulting equation is the inverse of the function. So here our function is y equals x squared. So if we switch our variables, instead of it saying y equals x squared, it says x equals y squared. That's the inverse. So to find out what y equals, we would take the square root of both sides. And that tells me that the square root of x equals y. These are inverse functions. Are they both functions? Well, they are the way we have them here. But remember, when you take the square root, you could have a positive or a negative square root. So if I'm looking at my calculator and I have graphed y equals x squared, okay, yes, that's a function. But if I go ahead and I go back to my home screen and I want to draw the inverse of that function, I'm going to go to draw and I'm going to draw the inverse. I want to draw the inverse of y1. Now, is my inverse a function? No, it's not a function because it fails the vertical line test. Could I have predicted that? Yeah. How could I have predicted that? Well, how did we know that the first one was a function? How did we know that this part's a function? Right, we did the vertical line test. We took that vertical line, we slid it across, all was well. Here it's not a function because we reflected it over the line y equals x, right? What happens when you reflect a vertical line over the line y equals x? Right, it's a horizontal line. So couldn't we have run a horizontal line test here? And if it failed the horizontal line test, that means it doesn't have a function. So that's why when we talk about our square root functions, we don't say plus or minus, we just say the principal square root. The principal square root is the positive one, so that when it's graphed, you can see it still is there, it's exactly on the inverse, but it's the red part. Notice it didn't cover the bottom. That's why we only deal with it, because it restricts the domain. The equation for an inverse of this function would be y equals 1 divided by x, and then the minus 2. So this function looks like y equals 1 divided by x minus 2. So what we want to do is solve this for y, right? So we switch x and y. So we've got x equals 1 divided by y minus 2. So we add 2 to both sides. So we have x plus 2 equals 1 divided by y. I want to get y by itself. Yeah, you can make it a proportion and cross multiply. So now I have y times x plus 2 equals 1. I want just y. Yeah, so you divide by x plus 2. And there's my inverse. And again, you can go back to your y equals on your calculator and check it. So if I go back to y equals and I take out that original equation and put in 1 divided by x and then plus 2, I don't need the square root anymore, right? And then I can go back to my home screen and just press enter again. And here comes the inverse. And it's so cool because you can actually see it like almost plotting each line, plotting each point. So you can see our asymptote for what was a horizontal asymptote at y equals 2 is now a vertical asymptote at x equals 2 because they reflected over the line y equals x. And we just talked about those graphs. Now, one of the other things we need to talk about is the fact that when we do the horizontal line test, that tells us that each x has exactly one y, but it also tells us each y has exactly one x. In this case, it would fail the horizontal line test because it would not, this y has two x's. Okay? When we go back here to these two functions, we found the inverses, right? It'd be nice to know, aside from graphing, how those are right. One of the things we do know is f and g are inverse functions. If and only if f of g of x equals g of f of x. So that being said, did we have any inverse functions in our original problems today? And the answer, of course, is yes. We did have inverse functions in our original problems today, because if you remember, those very first two that we did the compositions of, I'm sorry, let me finish where I was here. F of g of x has to equal g of f of x, which has to equal x. They have to equal x. So two functions are inverse functions if and only if f of g of x equals g of f of x equals x. They both have to equal x. So again, if we go back to those first two functions we composed, f of g of x equaled x, g of f of x equaled x, which means that these two functions up here are inverses. So if I solved for the other variable, I would have the other equation, which is a cool way to show two functions are inverses. Okay? So here it's asking us to graph the inverse. Well, if we graph the inverse, we could start by graphing the original function. We're going to have an asymptote at x equals 0, right? Because x can't be 0, so we're going to have an asymptote there. And we're going to have a horizontal asymptote at -2. Okay? So when we graph our function, we know our function is going to look a little something like this, because we know that that is the inverse variation function, and that's what it looks like. Now, if I reflect this over the line y equals x, what's going to happen to my asymptotes? Well, if I'm reflecting over the line y equals x, what once was a vertical asymptote is now going to be a horizontal asymptote. And once was a horizontal is now going to be a vertical. True? And so our graph is going to move also. So it's going to be more here. Oops, I meant to make that pink. So it's going to be more here and here, because those asymptotes changed. Okay? All right, so that explains how inverses and compositions are related to each other. It also explains how you can graph the inverses and the inverse functions together. All right, remember our job was to look at algebraic procedures to find composite properties and to derive formulas for composite functions. We did that. And we learned to use the properties of inverses and horizontal line tests to determine if an inverse function is a function. And we looked at how we could check to see if two inverses were inverses by using the composition function. So there's going to be some practice, but that's pretty much it.